So today we're going to talk about ellipses and hyperbolas, which are different creatures, but in an equation form, there's a lot of similarities. So there tends to be some confusion sometimes because they look so similar in their equation forms. Now, an ellipse, it's the set of points. Oops. Where the sum of the distances to two fixed points is constant. Actually, it's the set of points on a plane. I should include that because it's not automatic that you're on a plane when we say this. It's the set of points where the sum of the distances to two fixed points is constant. So how does that work? When I was in high school, I remember seeing this demonstration, and I think it's still probably the best way to do it. I can't physically do it here because I lack the tools. I need, for example, I need a cork board and things like that. But the way I remember seeing it, here's my two fixed points. I'm going to put them down right here. Okay, here's my two fixed points. Now I'm going to get a string, a piece of string that is longer than the distance between these two fixed points. So, and I'm going to tack the string to the end of each one. So the string is dangling like this. Okay. And then what I'm going to do is I'm going to take my pen. And so, for example, this point right here, if I pull it, I'm going to pull on it now. I'm going to straighten it out so that it's nice and tight. So maybe I'm here. So I've got that distance and I got that distance. The sum of these two distances is exactly the length of the string. The string is not changing its length because I'm pulling on it. Now, as I move this way, maybe I'm here. And as I move around, maybe I'm here and so on. So what's going to happen is I'm going to carve out a shape that looks like this, because if I'm pulling on the edge of the string, and I'm basically securing both ends of the string to these black points here, I'm going to carve out a shape, and the shape is not a circle. Okay, now I'm curious, just say it out loud. Did anybody ever see this sort of demonstration? Probably in high school. Anybody? Say yes if you did.
I saw it in my astronomy class. They explained this, how.
Oh, okay.
Yeah.
I think it is by far the best explanation, and it's the easiest to understand because the length of the string can't change, but it's not going to be a circle unless these 2 points are in the same spot. Then it would be a circle. Okay. Now, does anybody know what these 2 points are called? That is called a focus. That is called a focus. Together, they are. I always have fun with this one because my experience is most people actually don't know how to say that. It's kind of funny. Does anybody know what that word is?
Foci.
I like the inflection at the end. Does anybody agree with them? I actually learned there is a rule in the English language I learned when my kids were in elementary school. It's called the law of C's. Every word in the English language follows the same rule. And I'm not talking about proper nouns. You can pronounce your last name any way you want. But every word in the English language that has a C in it has the same rule. And by the way, it makes it easy to remember because there are certain words that you don't know how to say and go, oh, but wait a minute. It's like the I before E except after C. You remember that one when you're a kid? And I always point this out to people. Think of words, not California. How about cat? Century, city, country, cut. In the English language, if C is followed by A, O, or U, it makes a K sound. If it's followed by an E or an I, it makes an S sound. That's called the law of C's. I learned that when my oldest was in kindergarten and they were starting to read. I didn't know that was a rule, but now it made a lot of sense to me. This is called foci. If I wanted foci, I would actually have to use a K. It's actually that simple. It's foci is plural for focus. Now, you actually already know this. What's the plural for matrix? Does anyone know? Matrix. What's the plural?
Matrices.
Matrices, and that's CIS. What's the plural for index? Indices. Same thing as CIES. So plural for matrix is matrices. The plural for index is indices. The plural for box is boxes. Okay, that doesn't work. Have fun with that one. But you already know this. There's many words you go, oh yeah, that's right. I changed the way I say it. Yeah. So, and I always point that out because to me, it looks kind of silly when you're doing something and you're using a common vocab word and you mispronounce the word. It always makes it kind of look like you don't know what you're saying if you're using a common word and yet still mispronouncing it. You know, so if I was up here teaching and I said the foci, no, it's foci. All right. So with that said, that's the definition. Those two focal lengths that add up are constant. Okay. So how do I create an equation? So what we do is we do like we did last day. Let's create a picture where my ellipse is centered at the origin, and then I can move the center after I establish. Now, it doesn't matter if I make my ellipse go sideways or long ways. That's not really important. So for the sake of argument, let's just have it go more sideways. So my ellipse is going to look like, let's say, about here, the best I can here. All right. So there's my ellipse. It's not quite an egg because it gets vertical here. All right. So, and then my foci are somewhere here on the x-axis. Now, because of symmetry, and the center is at the origin, right? These 2 points should be equidistant from the center. These 2 points should be equidistant from the center. Okay, so we don't want to lose that. Let's call this point here a comma 0, negative a comma 0. Let's call this one 0 comma b. Hold on, I have a better 0 comma negative b. Let's call this one c comma 0 and this one negative c comma 0. So a, b, c, and d clearly are lengths. So I've moved c units, a units, b units. And what we want to do is not only get an equation, but establish the relationship between the a, the b, and the c. That makes it actually, exactly correct in the situation here. I'm centered at the origin. So now how do I do this? Well, we said the sum of the lengths is constant. So let's pick an arbitrary point on the ellipse. Let's call that point, how about x comma y? Okay, so make sure I got the right color here. So I have two different distances here. Okay, let's call that D1. Let's call that one D2. All right, so how do I calculate D1 and D2? So I'm going to erase this. I don't need the definition anymore. Now this process it's very algebraic. I would hope beyond hope that every single one of you saw this done both in an intermediate algebra and a pre-calculus class, because that's where you're supposed to see this, but you've probably long since forgotten it, so we're going to reestablish it. So D1, using distance formula, D1 is what? It's x minus x coordinate squared plus y minus y coordinate squared. So it's x minus negative c. So that'd be x plus c squared plus y minus 0 under the root. Okay. D2, that's this distance. That will be x minus positive c squared plus y minus 0 squared under the square root. Now, we don't know what to do with those quite yet. Probably at some point I'm going to need to square something. Okay, great. But those have to add up to a constant. So the question is, what is the constant they add up to? Well, remember, every point on the ellipse, think of that, the D1 plus D2, think of that as the length of our string. Okay. But that point right there, right there, a comma 0, if I take the distance from there to one focus plus the distance from there to another focus, that'll be the same as if I go from here. That'll be the same as if I go from here. Every point on the ellipse, when I add up the two lengths, those are called focal lengths, I get a constant. So let's start here. How far are these two focal lengths? Well, the first one's going to be a minus negative c. Okay. And the second one is going to be a minus, I'll put it like that, plus a minus c. This represents, if you will, the length of our string. This is the constant. This is what the two focal lengths add up to, no matter where I am on the ellipse. But notice when I add these up, it's just 2a. So when I put the string, I let it dangle, I went all the way around. Exactly how long is the string? It's exactly this long. That's what we just showed. From here to here is exactly the length of the string. Isn't that crazy? So that makes it really easy. That means that D1 plus D2 is 2a, and a is a constant that I know. I don't have to figure out a. A is there and there. I mean, I know a if I'm starting with my ellipse. So here's my equation. I really don't want to square both sides because that's just going to make it really nasty. So instead, we'll write it like this. And now we will square both sides. Because when we square both sides of that statement, it will become much, much easier. When I square both sides, I will get D1 squared equals 4a squared minus 4a d2 plus d2 squared. So no square root, still a square root, which means I will have to square both sides again eventually after I manipulate. So let's go ahead and fill in the holes here. What is the square of D1? Well, that will be x plus c squared plus y squared equals 4a squared minus 4a times this square root, which would be x minus c squared plus y squared, plus d squared, which would be plus x minus c squared plus y squared. Okay. This quantity equals this quantity. I'm going to get lots of canceling and lots of other things. So for now, I'm going to erase this. I'll draw it again later. I need this out of the way for the moment. Okay, so in order to finish this, I need to expand. I might as well do this right off the bat. Let's get rid of those guys. Okay, so now I'm going to have x squared plus 2cx plus, hold on a second. Turn this off. I hate phones ringing. Okay, plus 2cx plus c squared equals 4a squared minus 4a times my root, which is x minus c squared plus y squared. I can multiply it. I'll wait till later. Plus x squared minus 2cx plus c squared. So hopefully you see lots more canceling. I can cancel the x squared and the c squareds. Beautiful. Okay, now I've got that term and a similar term that easily will combine. I've got this guy and I've got this. I'm going to need to square both sides at some point. So what I really want to do is isolate the square root. I want the square root all by itself. And so in order to get the square root all by itself, I'm going to need to move things around. So what I'm going to do is I'm going to take this term and send it that way. And I'll take this term and send it that way. Then that means all the square root will be on one side and all the other terms will be on the other side. Okay. So when I do this, I'll have 4a times the root equals 4a squared minus 4cx. And I think that is, yeah, that's everything. Okay. At this point here, well, I think an obvious thing is get rid of the 4s. Every term has a 4 in it. So how about if we multiply through by a 4th? All right. One less thing I have to worry about. Now, let's multiply this out. I'm sorry, let's square this and then we're going to multiply it out. So I'm going to square this. It's the only way to get rid of the root. I'm going to square this, but I already got rid of the 4s. So this will now be a squared times. And what's this? A squared times what? Well, this will be x squared minus 2cx plus c squared plus y squared. On this side, I'm going to have, it's a squared minus cx, and I'm squaring the whole thing. I think that's what I got. Yeah. So that's going to give me, where are we here? So we're a to the 4th minus 2a squared cx plus c squared x squared. So let me go ahead and distribute this. So a squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared. That's the left side. Big yikes. I think I see one thing that's going to cancel. I believe these will cancel. Okay, now remember, A and C are numbers. So what I'd really like to do is get the X's and the Y's on one side and have the numbers on the other. That just makes more sense. So I've already got an X squared and a Y squared on the left side. So let's take this guy and send him to the left. And that's a constant. We'll send him to the right. At that point, we're going to be in really good position. So now I'm going to erase what we have up top here. I don't really need this now. So I said this algebraically is kind of intense. So what do we have on the left now? I've got a squared x squared minus c squared x squared. So I have a squared minus c squared times x squared plus a squared y squared. On the right side, I now have a to the fourth minus a squared c squared. That's a big yikes. Okay, so what if I factor this? How about if I write that as a squared times a squared minus c squared? Okay, that's an interesting thing. I've got the same two terms twice. So the last thing I'm going to do algebraically here before I go back to my picture, and this is something that probably you all remember from an ellipse, I really want the right side of the equation to equal 1. Not because that's special, but there's information. Kind of like when we did the parabola, we put it in the vertex form, x minus h squared plus, and then I could read things. When we talk about, slope intercept form of a line, if I put things in a certain way, I can read information. I would like this equation to equal 1. So that means basically I'm going to multiply through by the reciprocal of this. So if I do that, that's equivalent to just going like this. So now on the left side, I'm going to have x squared over a squared. This is one of those rare times we actually intentionally write it as a quotient with a denominator that's a constant, plus y squared over a squared minus c squared. And this is all equal to 1. That's starting to look more like what you remember an ellipse looking like. You got to getting in your Wayback Machine. So now a squared minus c squared, we need to figure out what is that. So let me go back to my picture now. And this will be beautiful. You're going to like this. So I created a picture where it was longer. Some things change if I make it, tall. So now we said, okay, that's c comma 0. That's a comma 0. And that was 0 comma b. Now we know that the sum of the focal lengths, we know that is going to be 2a. Okay, every point on the ellipse, if I take the distance to the two focal lengths, it's going to be 2a. Let's consider right here. Oops, should have stayed black. Because of symmetry, these two lengths here are obviously going to be the same because I'm coming from here. So if the sum of these two lengths is 2a, then that means this length right here is simply a. You notice I have a right triangle here. I have a right triangle, and right triangles have a Pythagorean relationship between their lengths. But in this case, my hypotenuse is the a. My height is the b, my base is the c. So in this picture, do you agree that a squared is going to equal b squared plus c squared? So that means that b squared equals a squared minus c squared. That's kind of cool. So this is what you probably all remember. That means that I can actually write my ellipse in this form. Again, I already know these values. I don't have to calculate them. I know them. They're given to me. So the equation of an ellipse that is centered at the origin, mind you, it's going to look like this, where A represents basically how far am I moving left and right. B represents how far am I moving up and down. And the nice thing is, if the ellipse opened long way, it's still the same equation. The difference is, if A is bigger than B, then it's going to go this way. If B is bigger than A, then it goes this way. That's it. It's actually that simple. And you'll say, well, what about the Pythagorean relationship? Well, if it opened long ways, then B would be the hypotenuse. So the easiest way to remember this relationship right here, because technically, if I wanted C, what's the relationship for C? Clearly, C squared would equal A squared minus B squared in this scenario. But if it opened long way, it'd be B squared minus A squared. So how do you know which one it is? It's always the absolute value of that. So if A is bigger than B, I'd subtract in that direction. If B is bigger than A, then I subtract in the other direction. I got to kind of keep it positive. So it's essentially the absolute value of that. Whether it opens vertically or horizontal, doesn't matter. So now, with that information, what if we now want to move the center? So like we did with the parabola, okay? Let's pretend that I can draw it. Okay, that was awful. It's more like a Rolling Stone lips, you know. Okay, here's my center, but my center is no longer at the origin. My center is now at HK. My axes maybe are here. Oh, that changes everything. Or does it? Remember, if I have a horizontal shift of h units, I replace x with x minus h. And it's still over a squared. This is the generic, most general form of an ellipse. Now it's centered at h comma k. So that makes it much, much easier. Okay, that's just not that bad if I look at it from that point of view. Okay, so let me, one second. I'm going to create a problem here now. Give me one sec here. Well, actually, you know what? I'm just going to grab a textbook. I had it written down, but I don't know where I wrote it. So let me just I'm going to grab a calculus book and grab a random problem from said calculus book. All right, so I want an ellipse. Here we go. Let me write it down. So let's suppose I have, I have the following equation. Okay, I have the following equation here. This is the equation of an ellipse. Okay. Now, it doesn't look like what we just did a moment ago. No, because a moment ago we manipulated it like we did with the parabola. This is actually referred to as the standard form. It's x squared, x, y, constant 0. So this is an ellipse. You say, how do I know it's an ellipse? Well, over the next couple of days, that'll be more obvious. But you know it's an ellipse, first of all, because it's a sum of squares. If these coefficients were the same, then it would actually be a circle. Okay. The difference between the ellipse and the parabola only has one squared term, the ellipse has two. The difference between the ellipse and the hyperbola we'll look at later, but the ellipse and the hyperbola, it would be a difference if it was a hyperbola. So my goal here is to find everything I can possibly find. I want to find the center of this ellipse. I want to find that general equation. I want to know where the foci are located. Okay, so there's a few things, but how am I supposed to do it with this? Complete the square. Okay, you learned how to do complete the square in algebra, not to solve quadratic equations in general. No, complete the square is mostly used for conics. Okay, you used them in parabolas to find the vertex, for example. So in order to complete the square, the first thing I'm going to do is get the x terms together, the y terms together, and then I'm going to put that 64 on the other side because I don't actually need it right now. Okay, now, as you remember, you can only complete the square if a lead coefficient is 1. So we're going to have to factor out the constant. So this is now 4 times x squared minus 8x plus blank, plus 9 times y squared minus 4y plus blank. Now, eventually, negative 64 plus blank, oh, so I'm run out of room here, right, equals negative 64 plus, I'm going to have to add something here to complete the square, which means I'm going to have to add something to the other side, okay? Because you can't only add it to one side. Now, you remember this. This is 4 times x minus what? Remember, I take half of that number, and then I square that number. So there's a 16 right there. Okay? Here, plus 9 times y minus, take half of that number, and then I square it. I put the little arrows to kind of help you, where everything came from. Now, did I just add 16 to the left side? Anybody? Did I add 16 to the left? No, what did I add to the left side? 4 times 16. So I added 64. Did I add 4 to this term? No, I added 9 times 4. And if it helps you, think of it this way. I just added 64 here because when I factor out the 4, it got me to here. I just added 36 here. Okay, so then I need to add 64 and 36. I'll do it right here. That means negative 64 plus 64 plus 36. So this is equal to 36. I've got it in the perfect form, but I need the right side to equal 1 in order to be completely done. So when I multiply through by 1 over 36, this will become x minus 4 quantity squared over 9 plus y minus 2 quantity squared over 4 equals 1. Do you see a 9 and a 4? No, you don't see a 9 or a 4. What do you see? Think of the general form. You don't see a 9 and a 4. What do you see?
3 squared and 2 squared.
The 9 and the 4 don't figure in the calculations. It's the 3 squared and the 2 squared. Okay, so when I go to draw this thing, for example, I want to get an accurate drawing. I'm going to move left and right 3 units. I'm going to move up and down 2 units. I'm not going to move 9 and 4. Those represent the a squared and the b squared. Okay, so right now, I'm going to go ahead and get rid of some of this stuff so I have room. Right now, you can all tell me exactly where the center is. Okay, right now, where's the center of my ellipse? I'll just call it C for center.
4, 2, 4, 2.
4 comma 2. Now we'll figure out the foci in a second because I have to still calculate that little. Oh, you know what? I shouldn't use C. I'm going to write out center. I'm sorry. We use C for the focal length. So we'll write it out. Now, if I want to draw this thing, if the center is at 4 comma 2, okay. Okay, there's my center. The center never actually shows up, but I need to know where it is because that's my starting point. Now, that right there under the x squared says I'm going to move left and right exactly 3 units. Let me give myself one more. I'm going to move left and right 3 units. From the center, I'm going to go left 3 units, right 3 units, and left 3 units. That number says I'm going to move up and down 2 units. So there and there. Oh, my units are kind of big there. Okay, so now I want to get an accurate drawing. Something like that. Okay, I know that was not great, but that's what my ellipse would look like. Now, where are the foci located? Are they located horizontal from the center, or are they located vertical from the center? Anybody want to try that? You got
Horizontal?
horizontally or vertically?
Horizontal?
How come? Because that's bigger than that. That's it. This opens in the X direction because that number is bigger than that number. If those numbers were switched, then this would open long ways. So what that means is that my foci are located somewhere on that line. Now, how do I figure it out? Well, remember the focal length, the c squared, we said was the difference between 3 squared and 2 squared. So it's simply going to be 9 minus 4 or 5. That means my focal length is root 5. Okay, now what do I do with the root 5? Well, kind of like what we did with the parabola, I'm going to add root 5 to a coordinate. But which coordinate? I'm moving sideways, so I'm going to apply it to the x coordinate. So now I can say then that the foci are -4 plus root 5 comma 2 and 4 minus root 5 comma 2. Now root 5 is around 2.3-ish or something, so it's not going to be all the way there. It's going to be about there and there-ish. Okay. So we've got the center, we've got the foci. There's not much else to say. There is one more thing that I'm going to introduce in a moment, but that's not bad. So giving you the equation, you're going to tell me all the information. That's what you just did. If I give you the information, then you can turn around and tell me the equation. Sounds familiar. Sounds like what we did with parabolas. Now there's one more piece of information with an ellipse. There is a number, a numerical value that describes the shape of an ellipse. Say the shape. Well, for example, isn't a circle a special case of an ellipse? Yeah. Suppose I had the equation of an ellipse and one of the numbers in the denominator was huge and the other number in the denominator was really small. So for example, suppose I had something like this. I have x squared over 1 plus y squared over 100. Okay. Well, what would that look like? Well, that means I would move 1 unit in each direction. And then here I'd move 10 units in each direction. That's not too bad. So I'd have an ellipse that was really long and skinny. Okay. This is what the graph, equals 1. This is what the graph would look like because I only moved 1 unit from the center and then 10 units in this direction. So there's a numerical value that describes the shape of an ellipse, and it's called, right down here, it's called eccentricity. It's a very simple notion. It's a ratio. And what eccentricity is a ratio, but of what? Well, we have a problem because we don't have technically a formal name. This is something that always drove me crazy. It sounds made up, but if I go the long end, think the length of the string. In this case, it'd be that line segment right there. In an ellipse, that's actually generally referred to as the major axis. Now, I don't like that because an axis is a line, first of all. The word, like x-axis, y-axis, the axis of symmetry in a parabola. An axis is a line. This is a line segment. So calling it an axis, I think, is a really terrible description. Plus, I never need the whole length. I only need half of it. My A's and B's only represent, from the center on. So I like to call it kind of like, they call that the major. And technically, you'd say, well, then should that be called the minor? Actually, we don't even have it. We only have something called the major axis. We don't have a minor axis, but it really should be. I like to think of that as kind of like the elliptical radius in a sense. It's not, but I want you to kind of think about it like that. It's the longest segment I can draw from the center to the edge of the ellipse. Technically, it's half the focal, it's half the major axis, half the major axis. Eccentricity is defined to be the focal length over half the major axis length. Okay, and by the term major axis does not refer to the line segment so much as the length of the line segment, which is even more confusing. So in this case here, this is 1 squared and this is 10 squared. It's the number 10 I'm using. 10 is from here to here. I'm never going to use 20. I'm going to use just from the center out. So half the major axis. And again, I kind of like thinking of it as kind of like the elliptical radius, if that makes it easier to think of. It's not a formal term, but I need you to conceptually get it. So this is what the eccentricity is defined at. And horribly enough, we use an E. I think it's a terrible choice because E is probably the single most important constant in math and science. And we're using E as a variable in this case. I don't like that, but that's the universal, we're using an E for eccentricity. But couldn't my A, B's, or C's, couldn't they be the number E? Yeah, they could. That's why this is not a great choice. But in this context, hopefully we don't get confused by that. So the eccentricity is the ratio. Now, what's interesting is the longer and skinnier it is, okay, the longer and skinnier it is, the closer the focus is to the edge. If it were a perfect circle, then both foci would technically be at the center. It's called concurrent. So there is a range of values of eccentricity. Eccentricity will always be a number between 0 and 1. It can equal 0 when it's a circle, but it can never equal 1 because the focal length cannot equal the length of this. Remember, there's a difference of squares. So in this picture right here, my C squared would be 10 squared minus 1 squared, or 99. So my C would be the square root of 99 in this picture. That would mean my eccentricity in this picture would be root 99 over 10. Okay, the focal length. Now root 99 over 10, and by the way, this is not an extreme picture, but root 99 over 10 is approximately 0.995. And I think it's safe to say that's really close to 1. It's not possible to ever reach 1. Again, why? Because one of these numbers would have to be a 0 in order for you to reach 1. You can't reach 1. But notice in this picture, my eccentricity is really close to 1. So there's a really easy way to remember eccentricity. It's a silly way, but it's an easy way. This is supposed to be a circle. In a circle, the eccentricity is 0 because in that case, the focal length is 0. Why? Because the number under the x squared and the number under the y squared would be the same number. And that would be the radius squared. Okay, in case you forgot, if I wrote this, isn't that the same as saying x squared over r squared plus y squared over r squared equals 1? There's my A and B, they're the same number. Oh, okay, that's why it's a circle, yeah. And then my focal length would be 0 because r squared minus r squared is 0. In a circle, your eccentricity is 0. In one like this, your eccentricity is really close to 1. When it's perfectly round, your eccentricity is a circle. When it's really long and narrow and skinny, your eccentricity is really close to 1. Does anybody see the obvious way to remember it? If your ellipse looks like a 0, the eccentricity is essentially 0. If the shape of your ellipse looks like a 1, then your eccentricity is close to 1. I find that the easiest way to remember it. I know it's kind of silly, but the longer and skinnier your ellipse is, the more it looks like the number 1, and that means you're really close to 1. Okay, and a perfect circle, well, your eccentricity is 0. So eccentricity is just simply a number that describes the shape. Most of the time, your eccentricity is just somewhere in between. So in the first problem that we just did, this one up here, we found the center, we found the foci. The last piece would be to find the eccentricity. Well, the eccentricity, right, the half the major axis, in other words, the bigger of the two, the bigger of A and B was 3. The eccentricity was the focal length was root 5. So there's my eccentricity. Okay, that's never hard to find. That's actually always going to be relatively simple to find. All right, so let's try another one. This time, keep it simple here. Let's suppose, so here's what I want to do. I want to find an equation of the ellipse with foci, let's say, -2, 7, and -2, -1. With eccentricity equal to 4/5. Okay, that's all I'm going to tell you. I want to find an equation of the ellipse that have those two foci and that eccentricity. Now, when we say find an equation, I would leave it in the form where you can read the center. It is always correct to multiply it out and have the x squared plus y squared. It's always correct to do that. It's just never useful. So if I have it all completely multiplied out, I can't tell where anything is. So I don't find that form the best. Now, what do we know? From this information, we know a couple of really important things. There's one focus, there's the other focus. So tell me something about my ellipse. Anybody want to try? Tell me one thing right off the bat. My foci are located vertically. Anything? If you're wrong, I'll throw things at you. So, don't worry about being wrong. I'll just hit my computer screen when I throw things. I have foci that are located vertically. So tell me something about my ellipse.
Your eccentric is going to be
taller than y.
Well, don't worry about the eccentricity. Just tell me something about my ellipse.
It's gonna be long ways.
Yeah, it's going to open vertically.
Yeah.
Because the eccentricity, excuse me, the foci are vertical. So that means my ellipse is going to be this shape as opposed to horizontally. An ellipse, you say it opens horizontally or vertically. There's kind of a loose way of saying it. Now, you now know what it's going to look like roughly. You know it's going to go like this. Can you tell me where the center is? Can you tell me exactly where the center is? What do you think? Where's the center going to be?
Six.
I need a point. Where's the center going to be exactly?
-2, 3.
And how did you get that? What is that? That's the what?
Well, it has the x coordinate of the foci. It's the average of the y coordinates. Yeah.
There's another word. We're talking about points. How about the midpoint?
Yeah.
It's the midpoint. Because of symmetry, that distance and that distance have to be the same. Oh, okay. In fact, that distance is C. That's what C is. C is the distance from the center to the focus. So I now know the center. Well, why is that important? Because now you can tell me the equation of the ellipse. I'm going to put something squared. Something squared. Now, if this is -2, 3, then this will be x minus -2 squared. This will be y minus 3 squared. Well, you know what? I'm halfway there, aren't I? I haven't really done anything. This is now the form of my answer. I still have to figure out what the numbers are. Okay, the number under the x and the number under the y. Which one is going to be bigger?
Y.
The one under the y, because it opens this way. Now, I need to figure out that number. Now, I know that the eccentricity is the ratio. In this case, it'll be the b value over the c value. Because I'm sorry, I said backwards, sorry. C value over the b value. Now, what is the value of c? It's exactly 4, isn't it? Is that exactly 4? Yeah, well, that makes it easier. So if C is 4, what does that make B? If the value of C is 4, and this ratio is 4/5, what does that make the B?
Is it 5?
Yeah, you guys are thinking too much. Doesn't B have to be 5? By the way, This doesn't, the ratio being 4/5 doesn't mean C is 4 and B is 5. It means the ratio is 4/5. What if C was 40? Well, then B would have been 50. What if C was 4,000? Then B would have been 5,000. So in other words, it's the ratio is 4/5. But the fact that we can clearly see that C is 4, that makes B clearly 5. Almost done. What was the relationship? C squared, in this case, is going to be the B squared minus the A squared. Sorry, C squared, which is 4 squared. What does that make?
It'd be 9,
So 9, so A will be
3.
3. So this will be 3 squared. And now we're done. That wasn't that hard, was it? So if I have the foci, then I automatically have the center because it's just going to be the midpoint. Now that I have the center, I have the focal length, I have the value of C, but I would need more information. Just giving you the foci is not enough. I needed to give you the eccentricity so you had the ratio so you could figure out what another length was. Once you have 2 of the 3 numbers, A, B, and C, once you have 2 of the 3, you got the third one because of the Pythagorean relationship. So that's it. So why do we study ellipses then? Well, it turns out it's quite useful for a lot of reasons. And this goes back historically, but it's also in a practical sense today, because we know, and again, we don't know because of a calculation, we know because of observations. Okay, we know because of observations, but we'll keep it really simple. You know, here's the sun, right? And here's us. Here's us. So when we go around the sun, it's really close. It's really close to a circular orbit, but it's not a circle. It's never a circle. And in fact, the further away you get from the sun, the more extreme probably it becomes. How do we know? What physical evidence do? Today is April 28th, and it was light when I got up this morning at 6. It was already light outside. Is that a big deal? Well, in December, when I got up outside, it wasn't light outside. It was dark for at least another hour. Sometime maybe around June, it's going to be light for 14 or 15 hours. But in December, it's only going to be light for about, I don't know, 10 hours maybe. There is evidence that we don't have a circular orbit. Okay, there's 2 things going on here. One of them is the fact that we have seasons. When is the Earth technically the closest to the sun? Does anybody know? What? Not so much the date, but give me a day. What day of the year is the Earth closest to the sun?
On March, right?
Actually, no.
Is it July or
December?
June or July?
Day,
August or something?
first day of winter.
Oh, it's one of the.
The first day of winter is when the Earth is the closest to the sun. When is the Earth the furthest from the sun? First day of summer, and they're not the same distance. You say, wait a minute, but it's backwards. So why are the days longer in the summer? That's because the Earth is tilted about 22 degrees. So the Earth being tilted and the fact that it's an elliptical orbit is why we have seasons, which is why the lengths of the days and nights are not the same. But the fact that we know the elliptical orbit exactly, then we know exactly when things are going to happen. We know exactly when things are going to happen, like full moons. We know, everything that's going on. We know when there's going to be an eclipse. How can we know there's going to be an eclipse in 3 years? Because we know exactly how the orbit is moving. We want to fly to Mars. I'm serious. We want to send a spaceship to Mars. If I know, let me put the sun over here. Okay. All right. Here's us. And maybe here's Mars. Now, we're right here and Mars is right here. Do we want to try to go to Mars right now? I'm sorry. Mars is right here. Do we want to try to go to Mars? Oh, heck no. What do we want to do? Because these orbits are independent of each other. What do we want to do? We want to wait till we're closer together. Maybe we want to go maybe when we're here and here, or something like that. So because we know exactly where Mars is going to be every moment, every day for forever, because we know their orbit, we know where we are, we can actually say, okay, on this date, that would be when we want to fly because the distances between them will be minimized. Now, if that date is too far in the future, we'll just pick a date that they're closer together because we can do that. We know the elliptical orbits. So it's a practical thing from a space standpoint, but it also means we can work calendars. We know seasons. We know when things are going to happen based on the elliptical orbits. So I think that's a really cool thing that we know stuff like that. Now, I've always found this incredibly fascinating. We know we're in an elliptical orbit, and we know exactly where one of the foci is. You might want to guess where one of the foci is?
The sun.
The center of the sun is one of the foci. Problem is, where's the other foci? Where's the other focus? It turns out the other focus is not even completely removed from the sun. It's like right there. There is no physical object. In fact, we know all of these planets have elliptical orbits. We know the moon has an elliptical orbit around the Earth, but there's never a second physical object that serves as the focus. Because thinking gravity, when we send a ship out there, we've got to escape the Earth's gravity, so we've got to go really fast. But if we don't go fast enough, that thing is just going to be stuck in orbit forever. I mean, we actually have satellites going around the Earth. They're in orbit, more or less, forever. They're not going anywhere. So once something's in orbit, it's pretty much going to stay there. It's not going to get closer to the Earth. It's not going to get further from the Earth. The gravitational pulls are now at a nice equilibrium. I mean, everything works nice. But the fact is that there's no physical object creating a gravitational pull for a second thing. I always found that to be really fascinating. And one of the things I find really, really interesting is planets with multiple moons, like Jupiter and Saturn. The moons don't all go in the same direction. The planets in our solar system do not all go in the same direction. It's weird. And we're not all on the same plane. We're all on completely different planes. So the idea of planets lining up, do you know that you can never have more than 3 planets in a line? It's not possible because all of our planes are different and distinct. But we can actually calculate when things like that are going to take place. Now, one of the things I find truly fascinating about this, so I took an astronomy class when I was in college. It was one of my favorite courses. I learned so much. For a while, I could actually look outside at night and tell you all the important things in the nighttime sky. But that was so many thousands of years ago. We've created a couple of new planets, I think, since then. And well, actually, things have changed. I mean, Pluto, I'm still kind of upset about that. Pluto was a planet most of my life, and then it got demoted, as a lot of you guys know that. Pluto, I don't know what Pluto did to piss off the astronomical world, but to get demoted from your planetary status has got to be so embarrassing. But there are things way out there where Pluto is and beyond. And I learned this when my kids were in school, the difference between things like asteroid, meteor, comet. They're not all the same thing. A lot of people think they're the same thing. And I've learned this because in the world of elliptical orbits, if you go to the Rubin H. Fleet Space Center, they also have things about that. Does anyone know the difference between a meteor and an asteroid? Are they different or are they the same?
Is a meteor
Is it where they're located? Oh yeah, you go.
They are the same. When does an asteroid become a meteor?
when it goes through the Earth's atmosphere?
Exactly. Oh, so in other words, if it's an asteroid, it's okay, but once it becomes a meteor, oops, I mean, it's just going to hit us. So there's always that speculation, will we get clobbered by a meteor? Now, a comet, you grew up, comets are these, balls of flame and everything. Actually, comets are frozen. Comets are big ice balls. They're not big flame balls. Now, there's something that happens, and this is one of my all-time favorite facts that no one will ever give me an answer to. Every 86 years, going back over 1,000 years, there's a comet that will come out of nowhere, slingshot around the sun, and then leave. Now, if you've ever watched Armageddon, I love that. They actually got the science actually pretty accurately. So you guys remember that's where Bruce Willis and the boys go up and they, take care of that asteroid. So as long as you're not heading towards the sun, the gravitational pull will have this effect and it will slingshot you. So you have this thing, this frozen thing. Now what happens is the closer it gets to the sun, that's why it flames up. It's not that it's on fire, but now it's, we're able to see things that we couldn't see before. And then it goes, now clearly the sun is one of the foci, but it takes 86 years. So imagine how far away it gets. It's completely out of our solar system. The question is, we know the day it's going to be back. What brings it back? It can't be the gravitational pull. It's going in the other direction. Does anybody know what this guy's called? It happened, I think, last time around 1990-ish.
Is it Halley's Comet?
I have fun with this one because all Americans mispronounce it. It's Halley's Comet. What's really funny is the last time Halley's Comet entered, and where we could see it, a news reader, I call them news readers because they're usually not the smartest people, it's like literally anchorman kind of people, was reading it and said Halley's Comet because he didn't actually know what it was. And now most Americans believe it's called Halley's Comet. For 1,000 years, it's Halley. Sally, Valley, Raleigh. I have a niece named Haley, and it's spelled very differently than that. But the funny thing is because the news reader read it wrong. Every time somebody on the news reads something wrong, I remember the Clarence Thomas when he was going through his stuff to become on the Supreme Court. This is around like 1990-ish, and there was all these Senate inquiries. I mean, all these things were going on, and he was accused of sexual harassment. It was a big deal because he's a Supreme Court justice. One newsreader read sexual harassment. And literally the next day, that was a word that everyone was using. There is no word in the English language to harass someone. It's harass. And all you have to do is look at how it's spelled. But for the last 30 years, I've heard educated people say harassment. That's not a word. It's not even close to a word because one person on the news read it incorrectly and a whole generation follows. That makes me laugh. It's still Halley's Comet. It's never been Haley. My niece would be upset because she spells her name different than that. But anyway, comets follow the same planetary motion that planets do. It's just that their focal lengths are so much further apart. But the fact that there have been comets, big deals, and I don't know if you guys have ever seen one, but it's kind of cool when you'll hear on the news there's a comet approaching and you go outside and you can actually see it maybe for an hour or two. There have been a few times in the last maybe 10, 20 years that we could physically see comets. The last one, I think my daughter lives in Portland, and I know Portland was one of the places. Does anyone remember? I think it was last year.
It was the Neowise Comet.
What's it called?
Neowise.
Neowise. I think, was it last year or the year before? I can't remember.
It was last year.
People were traveling just so they could go see it. And it was, because there were not that many places where you could see it. We couldn't see it from San Diego. And no big cities could typically see it because of all the light pollution.
You could have seen it from San Diego. I saw it from Imperial Beach.
Oh, okay. Because I've heard there were places where you had this incredible view. But here's my point. They knew exactly the moment this thing was going to be in view. Why? Because of the mathematics of understanding the ellipse. I just find that to be really cool. Is it useful information to us on a daily basis? Yeah, probably not. But it is kind of cool that you know exactly when a planet's going to be somewhere. So if any of you guys are planning your next trip, to Venus or Mars or something, it does matter. Now, the last thing we're going to look at is the hyperbola. And the hyperbola mathematically is the trickiest of the bunch. Now, the difference between the ellipse and the hyperbola is not the sum of the focal lengths that remains constant, but it's the difference of the focal lengths. So I have two foci, and I'm going to have a point. Let's say, here's a point. Now, if I take the difference of these two focal lengths, that will be a constant. So that means that as I move, maybe now I'm over here, or maybe now I'm over here, and different things, I'm going to end up kind of doing something like this. But I also have points that can be on the other side. So any point here, it's the same thing. The difference of the focal lengths remains constant. So the definition of the hyperbola is similar to the ellipse. It's that from two fixed points, the difference of the focal lengths is a constant. Now, the way we set this problem up is exactly the same thing we did with the ellipse. And what I'm going to do is I'm going to fast forward it because it's all the same algebra with a sign change in the middle. So a lot of the stuff we did before, it's going to be exactly the same thing. So I've got, excuse me, let's say this represents one of the foci, this represents the other one, and I'm going to be centered at the origin just like before. But now this time my A is on the other side. The focal distance is further than the A. Okay, or did I do that? Yeah, I got that correct. So what's happening is they're going in this direction. I'm orienting it on the x-axis. I could just as easily do the y-axis. So we know loosely it's going to do something like this. We don't really understand where the equation comes from. We know it's going to be loosely like this because when I call that xy, I'm going to set up the picture and then like I said, I'm going to fast forward the algebra. Okay. This time D1 minus D2, because in my picture, D1 is the bigger of the two, is going to be a constant. But what constant is it going to be? Well, let's take the easy route. Let me take that point right there. So from there to this focus, A minus negative C is A plus C. From here to this focus would clearly be C minus A. Okay, everybody got that? Because C is bigger than A. So the focal distance from this point to here is C plus A. The distance from this point to this is C minus A. And this difference has to be the constant. A plus C minus A is, oh, that's what it was with the ellipse. It was 2A. How crazy. And then what we would do is, like we did with the ellipse, we would do this, and then we would square both sides. We will gather all of our terms. And so I said I would fast forward this for you. And so when we do this, let me go ahead. Sorry. So when we do this, what is going to end up happening for the horizontally opening one is going to look like this. Okay, where again, C was the focal length, and then A. By the way, on the hyperbola, we call that point right there a vertex. That's actually called a vertex. The focus is there, the vertex is there. Okay, so that's A, that's C, and the difference, A squared, C squared minus A squared. So let's just give that a name. Let's call C squared minus A squared. Let's just call it B squared. There's no B in my picture. I mean, this is what it looks like. It looks something like this, but let's call it B squared for now. Okay. Then it kind of has the same form as the ellipse. Now, the difference is in the ellipse, the bigger of these two numbers determines the shape. In the hyperbola, it's easier than that. This is x squared minus y squared. It has to open horizontally. If it's y squared minus x squared, it has to open vertically. So with the hyperbola, the difference of the squares, whichever one's first determines the direction of opening. That's it. So if it's x squared minus y squared equals 1, it opens horizontally. If it's y squared minus x squared equals 1, it opens vertically. It has nothing to do with the sides of A and B. Now, there's a major factor now that I show in Calc 1. Some of you saw this if you're in my Calc 1 class, but I don't expect you to remember it. Let's consider, centered at the origin, let's consider the following hyperbola. Okay, let's consider this hyperbola. We're going to move the center to HK after we establish this. Let's consider this. I would like to graph this. Now, when I taught intermediate algebra, I would actually have them graph ellipses and hyperbolas. They didn't have to be perfect, But then I would sketch graphs and then, put them on graph paper and turn them in. And the graph I sketched by hand was significantly better than the one your graphing calculator could do, because simply asking the graphing calculator to graph it was difficult because it's not a function. So if I wanted to graph this, let's just say by hand, I would need to solve for y. So let's solve for y. So y squared over b squared equals x squared over a squared minus 1. Okay, so if I'm looking at that, now let's factor out, how about, from that statement right there, let's factor out x squared over a squared. Excuse me. And then I'd have, okay, no big deal. Now let's multiply both sides by b squared. So if I want to know what y looks like, well, a and b are positive numbers, so clearly that's just b over a. If I want to do the square root of x squared, technically I should be using absolute value of x, but I also really need a plus or minus, because right now this y can be negative. And then finally, because I just did the square root of both sides. If you do that, that is this. Now, why am I showing you that? Well, the moment I put the plus or minus here, I no longer need the absolute value, because the plus or minus is already taken care of that. So I'm going to leave it like this. Now look at that statement right there for a moment. What do we know about this guy? He has a name, because x is going to be allowed to get bigger and bigger and bigger. What's that guy called? Do you remember? A squared over x squared. What kind of term is that? Think limits. We haven't used it in a little while, but I know you all know the term. Starts with a T.
Transcendental?
Close. Transient.
Oh, transient.
It's a transient term. Transient terms are ones that become less significant. When you took, when you had the polynomials of different degrees, you multiply top and bottom by 1 over x to a power. Remember, and you got a whole bunch of terms with x's in the denominator, and that's how you ended up taking your limits easily. That's called a transient term. If I replace x with a fairly large constant, that contribution becomes negligible, meaning this quantity right here, as x gets bigger, not towards infinity, but just as x gets bigger and bigger and bigger, this quantity is getting closer and closer to 1. That's how we describe asymptotic behavior. So what does that mean? That means y is asymptotic, not equal. It's never going to be equal, because that's never going to be 0. But if I just put an x of 10, if I put x of 100, if I put x of 1,000, right, that contribution is microscopic. My hyperbola is asymptotic. This hyperbola is asymptotic to this, not because I told you, because I'm seeing it. So if I have the equation that looks like this, this is kind of interesting. And I said, well, same A and B, let's draw a line. So let's say that's B units and that's A units. Okay, so that's B units and that's A units. I've just drawn these two. I said this is asymptotic to those two lines. To be asymptotic to a curve is one thing. To be asymptotic to lines, that's the definition of asymptote. An asymptote is a line. Asymptotic behavior, I can have a curve that's asymptotic to a sine wave, right? First few terms of the Taylor series. I can have a curve that's asymptotic to e to the x. But if I'm asymptotic to a line, that line is called an asymptote. That's where that term comes from. So going back to my picture, if y is 0, then x is plus or minus a. That's how I know what's on there. So there's a0, and there's my negative a0. And my graph is asymptotic to these guys. So, and I'm guessing everybody in here learned how to graph a hyperbola similar to what I showed you, but you had absolutely no idea where the lines came from, because nobody ever told you, because your high school teacher had no idea where the lines came from. The lines come from me solving for y and proving that this and this are asymptotic to each other. Boom. That's where the lines come from in the hyperbola. A hyperbola, all you have to do to graph it accurately is put down your vertices draw your asymptotes, and basically these approach them. The common mistake that people have when they're thinking about hyperbolas is they're thinking hyperbolas are parabolic in nature. They're not even close to parabolic in nature. This gets straighter and straighter. In fact, if this had come to a sharp point, it would look like a V. The shape of the hyperbola is far closer to a V. It's definitely not parabolic in any way because I'm getting straighter and straighter and straighter. So that's one of the really cool things. Okay. Now, why do we need to know hyperbolas? Where do we ever use hyperbolas? I'll give you an idea. You use hyperbolas a lot more than you use ellipses in real life. All right. So here's how it works. Let's go back to a planet. Let's do planetary stuff. Okay, here's us, here's the United States, there's other countries. And down here, I have a friend who used to live in Australia, and he'd actually go to the Australian Open. I'm so jealous, love tennis. So Australian Open's on TV. We want to watch it. So what they do is, there's a satellite out here. Maybe there's another satellite out here. And then they send the signal here, but I got to be able to catch the symbol. Turns out the only way, signal, the only way to catch signals, the only way to catch radio waves or microwaves or different waves, it turns out is a hyperbola. A hyperbola is the only physical device that can catch them. Not the parabola, that was more for focusing. This is for, I'm retrieving. So what if I put a hyperbola maybe on my roof? No, the three-dimensional is called a hyperboloid. But what if I put one on my roof? I could gather these and I could charge people money to come over and watch the game. Oh, that would be a cool thing. I could maybe listen to conversations from space aliens with a really big hyperbola on my roof. Has somebody already beaten us to it? The hyperbola on your roof to catch waves? Anybody have a hyperbola on their roof? We actually have one on ours. We don't use it anymore. Direct TV. What am I talking about?
Satellite dish.
Satellite dishes. They're hyperbolas. If you have one on your roof, look at it. It's a hyperbola. Yeah, it's finite, but it's a hyperbola. Now, I want to talk to space aliens. Well, who would do such a thing? Anybody ever driven past Lawrence Livermore Lab or places like that? There are hundreds of giant hyperbolas pointed to outer space. Yeah, our government has spent millions and millions and millions of dollars on really big hyperbolas pointed to outer space to listen for conversations. That's not a joke. Yeah, hyperbolas are how I catch the frequencies, those waves. So it's a very cool thing. The hyperbolas, in other words, so that's how we gather. The military uses them all the time. That's they targeting things, or when missiles are coming at you, being able to figure out where the missiles are coming from because of certain wavelengths and things. So it can get very, very complicated. But hyperbolas are basically the foundation of it. That's a satellite dish. Okay. Now, the satellite dish is only one of the hyperbolas, but I only need one because it's pointing in one direction. The other would be now in the hyperbola, the actual circuitry, the thing that's catching the waves. So the hyperbola is there, but there's got to be something that's acting, the transceiver, the piece. It's exactly where the focus is. So the focus of the hyperbola is where you put your, so in my picture here, the focus was about right there. That's where you put your little device. And then the hyperbola does the rest. So it's kind of cool. I think parabolas are still more useful, but if you closed circuit TV, my picture actually is pretty accurate how it works, because I want to capture waves from around the world. It has to come back in. So what happens is the cable companies and stuff, if it's free, they're going to get it and then they're going to broadcast the signal to you. But let's say you wanted to watch, some fight that's on TV and you got to pay, your $50 or whatever. Then you have to have the ability to get this. So maybe you go to the sports bar and they have the satellite dish on the TV and they're going to, air the game, that kind of stuff. This is what happens. But this is a kind of a cool use of it. Anyway, this is a good stopping point. We are now done with conic sections.